J Austin Hughey. As you said, I work at Engine Yard. I organize the local Austin Open Hack chapter, Open Hack ATX on Twitter. Of course, Engine Yard is also on Twitter. If you're going to follow me, do so at your own risk, because I shoot my mouth off and I'm kind of an asshole. This is a talk about application servers. I kind of wanted to see what various different application servers in Ruby would do under certain different circumstances, and which one do you want to use? Because there's not exactly a shortage of them out there. I looked at 4 of them for this talk, and there's a lot more than 4 out there. I just wanted to see, in the case of 3 of them, they're pretty popular, so how they do, and one of them is rather. It says it's on. Can you guys hear me? Testing, testing. Weird. All right, I'm going to keep going because this thing's on, but whatever. Anyway, I wanted to see what these app servers would do under different circumstances. So that's kind of the idea here. And before I get into that, I'm going to tell you a little bit about a conference that Engine Yard is putting on called Distill. August 8th and 9th in San Francisco. We're giving a ticket away here, by the way. Just tweet at Distill on Twitter with the LSRC hashtag. Look at the conferences, the speakers, and tell us which one looks most interesting. And that's basically how you want to enter for a chance to win a free ticket. There's going to be 25 speakers. I think Jim Wyrick's going to be there as one of them. Konstantin Haas, if I can say his last name right, is there, as well as several other people that are experts in their field. The idea being just to kind of bring some best practices back to your organization: application architecture, UX testing, and security. So that is the shameless promotional plug there for everybody. But let's move on here and talk about these things. Like I said, I wanted to see what these things would do under various circumstances, and when to use one versus another. So I examined 4 basic things. It's mode of operation, the use cases behind it, configuration, what do you have to do to get it running, and performance. How does it do under pressure? So let's meet the gladiators in the arena here, if you will. Passenger is pretty common. Got a lot of widespread use out there. It's familiar to most developers, very easy to configure. Unicorn is also fairly common. It's one of Passenger and Unicorn are 2 main ones on Engine Yard Cloud. Uses in-memory forking to actually create a new worker process. It's for fast client request execution. You probably don't want to use this for something like live streaming. Thin, for example, by contrast rather, is event machine based. It does work well in that kind of situation. And Puma is the other one I looked at, which is an Engine Yard sponsored project, and the idea is we want to use threading and actual concurrency for the web server itself, and it processes requests on a new thread as they come in here, even on MRI. The arena itself is basically a little Sinatra app that I wrote. It's got 5 basic actions, and the idea of each is just to see kind of how does this thing work here with this. The server action just displays very basic information. Pi computes pi to 5,000 decimal places. And the idea is to simulate a mildly computationally expensive task. Sleep just sleeps for 1, trying to do kind of an I/O blocking kind of situation, sort of without actually doing I/O, as well as to create some request queuing. The Borat is probably my favorite because it uses the Twitter API to follow DevOps Borat on Twitter and just get the last 10 tweets from him. If you don't follow that dude on Twitter, he's actually rather funny. I recommend it. And the idea here was to simulate real-world network latency. And random, of course, does one of these at random, except for the Twitter one because of the API rate limitations. The hardware I did with this was high CPU mediums on Amazon EC2, which have 2 virtual CPU cores and 1.7 gigs of memory. This is all on Engine Yard's Gen 2 stack with the 3.4 kernel. And the code for this, as well as a rather lengthy description of everything I'm going to talk about here, is available at GitHub at that URL. So let's move on and talk a little about Passenger. I did this with Passenger version 3 because we don't have version 4 on Engine Yard Cloud yet. We're working on that. We've got a Gen 2 distribution team that goes and does e-builds and stuff. But yeah, this is with version 3, so bear that in mind. It's basically the way it works, its fighting style or its operation, since we're talking about arenas and gladiators and such, is that it embeds itself as a module into Apache, but Nginx doesn't really have a modular plugin-like architecture, so it has to be recompiled from scratch with Nginx, which means that you've got to grab the source code from Fusion and compile that source code in order to actually get this running. I think that where Passenger really excels is when it's trying to run multiple low to moderate traffic applications on the same hardware, because you can literally get more bang for your buck. It elastically scales the worker processes according to traffic and demand. For always-on applications or a dedicated application on that environment, that particular set of configuration, which is kind of a default, is not really ideal, but you can configure around that. There's no reason you can't. You can do per worker or global request queues. Usually global is a better way to go. You can manually route requests with that, just like with the per worker queue. And of course, it has a plethora of configuration options available to you. It's generally a pretty good all-around server. It's very compatible with pretty much everything. It's all around really quite decent. As I said, multiple apps on the same hardware is the best way to go. There are a lot of advanced features that Passenger has that are not available in their free product. You have to pay money for their license, such as multi-threaded requests on version 4 of Passenger. Puma can do that. Rolling restarts, zero downtime, Thin, Unicorn, and Puma can all do that. Although Passenger has a really cool feature that they call deployment error resistance. The idea is that they have, let's say you have 5 application workers running at any given point in time. If you say, I'm going to deploy my app, the Passenger master basically kills off one of those workers, spins up another worker of your application and says, oh, this crashed on boot. It doesn't work. It'll freeze those other 4 application workers on your old code base without actually spinning up new ones to replace them because obviously they don't work, hence resisting the deployment error. And of course, it locks it and logs things, so you have to go in and manually clear that out. One of the cool features it has in their enterprise, these are all their enterprise features, by the way. One of the coolest features that I think is actually really cool is you can attach to a PID with Passenger, one of their worker PIDs, and end up in a live REPL right there and be able to actually do some stuff. You can kind of fudge this a little bit with strace if you want. You can attach to a PID with strace and see like kernel level information, what's going on. But there's not actually interactive like an herb console would be or REPL. Its configuration is all Nginx. You can put it pretty much wherever you want. It's, like I said, compiled directly in there and with Nginx. You can configure multiple applications or just one. Either way is fine. You can pre-start application workers because Passenger by default waits until it needs a worker before it actually starts one. Waits for a request to come in, queues it, and says, oh, crap, I don't have a worker for this. Let me boot one up. So you can kind of spoof that a little bit with a pre-start directive that it has in its configuration. You can say how many workers you want with Passenger. You can configure that. But if you're using for an elastic situation, that can be very subjective. So I generally recommend start with take the number of cores in your machine, multiply by 1.5, and round up from there. But you might want more if those applications are low on memory usage. You might want fewer. It kind of depends because you could end up being CPU bound or memory bound. Either way is possible. So moving on, talk about Unicorn. I was looking for good images. And I thought, Robocop running a Unicorn, that has to go in there. That is too awesome to ignore. So, Robocop running a Unicorn, ladies and gentlemen. There you go. Yeah, it doesn't have a logo as far as I know. Anyway, so Unicorn's mode of operation is quite a bit different from Passenger. And the other two after this we're going to look at are fairly similar to Unicorn. What it does is it spins up a worker process that is a master process on boot. And then it only does that once. And it forks itself off into however many different workers you tell it to do. So it uses in-memory forking to create different workers. After that, the master process just kicks back, pulls up the newspaper and a cup of coffee, and just pulls manager and just watches all the different workers. It does not actually work any requests after that. Only the worker processes do. And for this reason, it has an interesting feature configuration option, the before and after fork blocks in terms of configuration. So basically, all the different workers pull from a single socket on the local machine. And so Nginx will put all of its different requests into that socket. And there's no singular thread or process that does all the routing. It's just all the stuff goes into that socket. The workers proactively, of their own volition, look at that socket and pull something off of it to work. Let's see here. Use cases. This is best for one single dedicated always-on app on one piece of hardware. It will kill workers that are running long requests. So by default, I believe it's 30 seconds. You can change that. In fact, our configuration has it set for 3 minutes. But you can change it. But at a certain point in time, Passenger's master process will be like, okay, this worker's taking way too long to execute a request. I don't know if this is in a bad state or what's going on. Kill it, fork, done. That's basically how it works. And on Engineer Cloud, we've seen a lot of situations where I worked on our support team for 1.5 years. And Passenger was the default on our platform for a while. And under load and high-stress situations, we saw a lot of situations where Passenger would behave just really, really weird. Made absolutely no sense what it was doing. It wouldn't log things. It would hang. It would log things that have nothing to do with the application. Just weird stuff. I'm hoping that Passenger 4 will never see that stuff again. I don't know. But I did notice that under load and under large production deployments, we did see less, what the heck is going on here than with Unicorn that we did with Passenger. Let's see. So the configuration for this, like I said, we have got before fork and after fork blocks, which are pretty cool. What I'm going to do here is actually go into, well, if this would work, SSH and show you guys. And just show you what the configuration might look like. This is just a host name that I set up like an Etsy host so I can see what's going on here. But the way we do it on EngineYard, for example, and I'm showing this not, just so you can like figure out, okay, this is how it works. Okay, now I can implement this myself however I want. But we use Monet, and I'm going to show you real quick here. Of course, we have 6 workers running in this case, and that can vary depending on how you want to run things. But we're using Monet to keep these things up, and we have a start-stop script that is basically a bash script that just goes bundle exec unicorn and gives it some options. But that configuration is basically in unicorn.rb, and we can see here several of Unicorn's configuration options. So you can tell it current path, shared path, working directory, how many processes you want. Listen tells it the Unix socket. Timeout, like I said, we have it set at 180 because we have some customers that have ridiculously long-running requests for whatever reason, but they want to use Unicorn, which is fine. Where to store the PID, and so on and so on. The cool thing here is you've got before and after fork blocks because, again, Unicorn says, okay, I'm going to spin up a master, I'm going to fork, and then those are going to do the work. So before fork, you want to do something. If, in this case, active record is defined, disconnect so you don't have a database handler that is shared among these different processes because otherwise you could have some really funky results there. And then, of course, that's just one thing. For example, in the after fork block, we're basically reestablishing that active record connection as well. And of course, if you have another database adapter of whatever kind, you might want to do that differently. Now, from the Nginx end, the way that we do things is pretty simple. We just basically dump all the stuff into an upstream definition and say, here is a Unix socket. Put all your stuff here. It's got one Unix socket, and that's it. The rest of it is pretty standard Nginx configuration. It essentially just routes the requests into that Unix socket using try files here, for example. If URI is there, try that. Try all these different things. Otherwise, last possible option, hit the actual app. So that is the configuration for Unicorn in a nutshell and how that works. Let's see if I can go back to this presentation here or not. So yeah, we just covered that. I recommend starting worker count like number of cores times 1.5 and then round up from there. As you saw there, this particular case we had 6 workers. It really kind of depends on whether or not you're going to be CPU bound or memory bound. You could be either one. It really just kind of depends. Next, I'm going to move on to thin. We don't really have thin support on Engineer Cloud. We just don't have it, which I think is kind of a mistake. I think we should. And in fact, what I did is I wrote custom chef recipes to basically take our Unicorn stack and overwrite it and shove thin in there instead. So all that source code is available on the GitHub repo I showed you earlier. So that's how I profiled this, and I'll show you that briefly in a minute. So the way it works is it's kind of like Unicorn, except it has one socket per worker. You tell it, I want n number of workers, and each of them has their own socket. So you might configure Nginx to round-robin balance between them. It's based on an event machine, so it could work pretty well in theory with long-running requests, stuff like live streaming in Rails 4, for example. And you can do rolling restarts with the 1-by-1 option. So it'll restart one worker, then another, and so on. So you get 0 downtime deploys with as long as you don't have like a database or migration that's going to break the app. Use cases, again, single app on hardware. It's better at long-running requests. Unicorn would be a bad mistake to use there. This would not. This would be a good thing to do. Its configuration, like I said, load balance at 1 socket per worker. YAML configuration file, I'll show you that in a minute. And of course, the num cores times 1.5.round is what I generally use for that. So the configuration for that, basically, come on. Looks like, damn it, there. All right, so you can tell it various different things like the PID, log, socket, rackup environment. How many servers you want is how many workers. In this case, I have it set to 3. We don't have to do 1-by-1. Group and user. And this thing, I like this last option, this tag option. Basically, if you look at PS output, you'll see right here it's got that tag in there, the last argument there, thin app server arena is what I call it in this case. So you can actually give it a tag and it'll show up in PS output for the workers. Now notice here also there's no master worker. I told it I want 3 workers. There are exactly 3 thin processes running. There isn't a master. So if we look at, for example, netstat, we can look at the bottom and see the different sockets here, and you can see, there's the path to the actual socket going on here. So in this case, var run engine yard. Nginx configuration is very similar, but has multiple definitions. Where am I? Here we go. So in this upstream, we've actually basically defined 3 different servers here in this upstream. So Nginx should go through a load balance round robin thing. First request here, second request here, third request here, fourth request here, fifth request here, sixth request here, and so on. So you should be able to kind of pseudo load balance that way from the Nginx perspective. It's not actually like real load balancing requests to different servers, of course. You could do it that way. But that is, in a nutshell, how this thin configuration is set up and working. Okay, moving on to Puma. This is a concurrent web server for Ruby. It's an engine yard-sponsored project, and the idea was basically to build an application server that executes each request inside of its own thread. Now, threading is a discussion well outside the scope of this talk, but basically in a nutshell, you on Ruby have this thing called the global VM lock or the global interpreter lock, and it essentially guarantees that only one actual Ruby instruction of code will run at a time. So even though you have the thread class in Ruby, it's not actually doing real threading, unless of course you're using an alternative interpreter like JRuby or Rubinius, which do not have that GVL limitation. So that is something to bear in mind here. Now Puma, basically because it does, threading is really the key concept here. It will still try to do it on real threads. Even on MRI, it'll use the threading capabilities there to the best of its ability. It binds to a ports or socket. Basically, there's one socket for all of its workers, kind of like Unicorn, and it runs each request in a new thread. Anything that can benefit from truly concurrent execution is fair game to give it a try. I think Puma is kind of a younger project, so you might want to try it out first before diving in deep. But computationally expensive tasks, to my surprise here, to some extent anyway, didn't really work so well. And I'll show you this in the test here pretty soon. But I found when I was computing pi with this that it fell over on its face hard, like really bad. It performed horribly. And I was really surprised by that. If you're using JRuby or Rubinius and you have only just one processor worker, one worker on the entire machine, no matter how many cores you've got, because it can do real threading, you can save a lot of memory by doing it that way. And Puma can do rolling restarts as well. Its configuration, like I said, one socket for all requests. You can do rolling restarts by sending the master process a user1 signal. And of course, you can specify how many threads min and max when you're starting Puma. And I will show you that momentarily as well. As soon as SSH cooperates. All right, cool. I'll go from the outside in this time. Nginx, servers, and this. So here is the basic configuration. Just like Unicorn, same exact thing. All we've got is one server definition in the upstream, and that's it. It just points to a Unix socket, and you're done. We look at the, this control script that I wrote. Because our default, what did I do here? Thank you. The screen's kind of dark right now, I'm trying to save battery power. Anyway, I just wrote a very simplistic bash script to do this because I kind of ripped out our stack a little bit and wrote it a little bit differently because Puma support is experimental on Engineer Cloud right now, and they're binding it to ports, and I wanted to do sockets because there is some documentation that claims that sockets can increase performance by as much as 10% or more. So I said, let's go sockets on this. So I rewrote the script itself. Basically, all it does to start it is just cd into the directory the code is, and then run Puma with an environment framework, passes a PID file where you want it to go. The the number of threads. In this case, I've got set to 416. Is that 16? Yeah. Like I said, the screen's kind of dark here. And 2 workers in this case. And that is, I kind of did Puma a little bit of a disservice here by setting it to only 2 workers because I'm running all these tests on MRI Ruby 2.0. Which, of course, has the global VM lock. And Puma is not going to really be able to do justice at that point. But I wanted to keep parity between the different interpreters involved here. And I also, for the sake of experimentation, wanted to see, even though I know it's a little bit gimped, I want to see how close to the same performance can I handle with just 2 workers as opposed to like the 6 that Unicorn has, right? So same deal here. We're just binding to a socket. Here's the log file and so on. Pretty simplistic stuff. And of course, this is also under Monet as well. And so you can see there the different things there. The 5001 and 5000 are from the old stack that I basically ripped out. So that is configuration for that in a nutshell. Just give you an idea of how that's being handled. So let the games begin here. How did they perform when they were hit? So I used this tool called Siege. I was originally using Apache Bench, and then I found that Apache Bench just plain doesn't work for me. It's broken, really, really broken. I found bugs in there that had been reported in 2003 and last looked at in 2007. I was in college in 2003, and that was a while ago. So I was not real happy about AB, so I moved on to Siege, and it's actually a really cool tool. You can do a lot of cool stuff with it. And I've got the details at the README at the GitHub repo. Well, let's start out with the Borat action, because I love Borat. Basically, I was going to put these graphs inside the presentation here, but I just didn't find a way to do it very easily or simply. But so what I did was I took Siege's output, which, let's see, where did I put the... Oh, this is the application, by the way. This is the thin, for example. You can see the server information. I told it, this is thin. It figures out what app server it's running under, process ID, Ruby version, the engine involved, and the platform. And, of course, some request information here as well, the environment variables for the request. So, of course, that's the same for all these. Here's Unicorn and so on. Let's see here. Screen resolution is ridiculously small. Come on. I wonder if I can do this. That might work. So I'm just going to show you guys an example of the Siege output so you can understand what's mapped to what here. And okay, yeah, sure. Let's work. All right, so here's an example of clean output from Siege. It'll tell you how many transactions, the availability here as percentage, how long it took to do the entire test. And basically what I did here is I said, I want 100 concurrent connections at a given point in time, and I want you to run this test 1,000 times, which results in 100,000 hits. So it's a pretty good sample size to see what's going on here. Tells you the average response time, transaction rate, how many happen per second, the concurrency. According to the Siege man page, as the concurrency rises, how many requests are executing at the exact same time. That's decreasing server performance, because in theory, you should be able to execute them really, really fast. So the longer they take to execute, of course, the higher the concurrency goes. How many successful transactions, how many failed, longest and shortest, and so on. So that's basically what I have mapped over to this spreadsheet and generated graphs with numbers here. All these different things for the different tests. So Borat, I only did 50 actual transactions here because I didn't want to get smacked down by Twitter's API. So this is probably not the fairest test. But in general, of course, they all succeeded. They were all very quick. The elapsed time here, of course, the delta is not very much. This is seconds. So 2.7 being the highest, 0.8 or 675, or is that an 8? Being the lowest. You can see there's not a whole lot of difference here. So that's not really fair to even judge it based on that. Transaction rate, a little bit more difference here. Passenger and Thin basically kind of had the lowest transaction rates. Puma had the highest, and of course Unicorn is kind of in between there. The concurrency, of course, the higher the concurrency is, the lower the performance is, because it's all happening at the same time, whereas it should happen much faster. If you see here, the Unicorn and Puma performed best, followed by Thin. Passenger came in behind. They all succeeded in their transactions. None of them failed. The longest transaction was shortest on Puma, and Unicorn followed there, and then, of course, Thin and Passenger. So Passenger didn't do so great in this particular test, but that's only one, and it's not very fair. So let's look at the pi test. Here we're computing pi to 5,000 decimal places. I originally wanted to start with 20,000, but hitting 100,000 requests, yeah, that didn't work out so good. Everything fell over, and it was just not enough sample size to matter. So we look at the transactions here. How many times the server actually got hit? Notice that Puma and Passenger never even made it a quarter of the way through the test before they exploded and fell over. And Siege was like, at one point, it's got a built-in throttle. It says, okay, I'm going to stop at this point. It basically gave up. So, however, Unicorn and Thin both finished 100%. If you look at the availability, of course, is that. Elapsed time. Thin took longest, followed by Unicorn. Puma and Passenger just throw out because they didn't even finish. If we go on to the transaction rate, higher is better. Unicorn led the transaction rate here. Of course, it's got 6 workers going on there as opposed to my 3 with Thin. So that may have something to do with it, though I'm not entirely sure because of the test like pi computationally, you should be CPU bound. So maybe it might make a little bit of a difference. I'm not sure. Again, concurrency higher means not as good performance. Successful transactions, all 100,000 succeeded for Unicorn and Thin. Passenger and Puma failed, as we know, so that's failed. And Unicorn had the shortest, longest transaction, a little over 10 seconds. Thin basically had, I guess that's 25 seconds roughly for the longest transaction. The shortest transaction was won by Thin, no doubt. Let's move on. I'll do random last. Server just gets that server page I was showing you earlier. This is probably a pretty good test here. So they all pretty much finished. I mean, Passenger got to 99,977 transactions roughly before it fell over, which is okay. That's fair. That's fine. The other ones finished 100%. That's reflected in the following graph. Elapsed time, Thin definitely won here. It was fastest, followed by followed by Puma or Unicorn. They look pretty even. Transaction rate, of course, we've seen that. Concurrency, of course, Thin apparently didn't perform that great because, again, higher concurrency is less performance. Puma seems to lead the pack there. Successful transactions, we've seen that. Failures, longest transaction, Thin won that, and the rest of them were pretty much on par with the minimal speed of transaction there. The sleep action, sleeping for 1 second, also yields some interesting results. With Unicorn, all requests completed, although it took forever. Passenger didn't do so well. Puma didn't do so well. Thin just completely crashed. It only completed, if you look at the actual numbers, Thin got through only 66 requests before Siege was like, yeah, whatever, I'm giving up. So, yeah, availability obviously reflects that. Elapsed time, same thing. Unicorn just took freaking forever, several hours to finish this test. Transaction rate, of course, is highest on Puma, which is somewhat understandable because it's going to launch a new thread for that. Concurrency, of course, lowest on Puma, again, because it's going to launch a new thread for each request. Unicorn is the only one that finished them all. So yeah, that's basically it in a nutshell. Now, the random action basically has a 50% chance of getting that server that I was telling you about, that server page I showed, and the rest of the different items, varying chances there. The idea with this is to send 100,000 requests and just see, let's simulate user behavior for an app that has multiple functions. So you might be checking out the server page, you might be computing pi, you might be doing something else. Now this particular test surprised me very much because Puma fell on its face hard the first time I ran it. Only completed 19,000 requests out of 100,000. I thought, that's really weird. This is random, so it's theoretically possible it got an inordinate number of requests for pi because we know it failed on pi really bad. So maybe this is not fair, quote unquote, to Puma, so let me run it again. I ran it again, results were duplicated. It only got barely over 20,000 requests before it fell over the second time around. So that's why we've got an extra row here. But we can see the results here as well. Transactions, again, Thin and Unicorn won. Passenger also fell over, but it got pretty close. Puma failed miserably. So availability, Unicorn had the highest availability rating, followed by Thin and Passenger. Last time, Thin took much longer. Unicorn cranked those out pretty fast. Now, again, these are random, but the sample size is 100,000, so take it for what it's worth there. Transaction rate, of course, Thin had the lowest transaction rate. Puma had the highest for understandable reasons, but that doesn't really matter. Concurrency, same thing. And successful transactions, both Unicorn and Thin won that. Thin had a few failed transactions, but not terribly many from the looks of things. Unicorn definitely won in terms of the longest transaction. So that is how they performed in a nutshell. Based on this data, I would basically say that the initial assumptions I start off with about use cases for these things, Passenger definitely is going to be best in your multiple application situation because it'll spin up a worker when it's needed and kill it off when it's not, when there's not enough traffic to justify it. Unicorn and Thin seem to be roughly on par. But you might have to decide, okay, do I want to use Unicorn for a live streaming application? No, not the way to go. You probably want Thin there. Puma, unfortunately, I don't know if I can really recommend it at this point. I think it's okay for certain things, but I don't really see it based on the results of these tests. I don't know. Although it would be fair to say that because this is running under MRI, that may not be entirely fair to Puma. And you can see in some of these tests, you can see that in spite of its only having 2 workers and running on a GVL addled interpreter, it still performs roughly on par with the other application servers out there as well. So that I think Puma's got a lot of promise. I think probably just needs a little bit more work and exposure to live production applications. So that's it in a nutshell, guys. Questions?